Hi everyone, thanks for checking out this video. And also, sorry I haven't made a video in a while. I've kind of been like really busy with grad school and research lately. But yeah, I thought I'd make another one today, just another video to get some more practice with this topic of parameter estimation I've been covering recently. I've done a couple of videos on this already, like how to estimate parameters of different kinds of models. And this is just going to be more practice with that. I think a good way to get good at this topic is to just like keep practicing a bunch of times, kind of doing the same thing with like different kinds of models. And today is going to be about how to estimate parameters for the logistic growth model, which I've covered this in some previous videos. So the logistic growth model is a model of cell population growth. Really, it's really a model of like, I guess, any kind of population growth, like including cell populations. Could also be like an animal population or like even a human population. But for our purposes here, we're going to be talking about using this model as a model of a cell population. So I thought I'd like kind of do what I've been doing with these recent videos and kind of showing you guys like an example data set and talking about how we would fit the model to this data, and then show you guys how to do the fit in Python. So let's just say that we get this kind of a data set from a biologist. Let's say they send us this like time series data of an experiment they did where they grew out a cell population and measured the cell counts at different time points. So I have this plot here of cell counts as a function of time, and we can see that the data is kind of noisy, so this could be partly just like due to like the biological noise, and also we could think that this is like partly due to like experimental noise too. But we can see that even though it's a bit like noisy data, it does have this logistic looking like shape to it, where it starts growing like almost exponentially at first, and then it kind of hits a carrying capacity and then steadies out. So let's just say we get this data from a biologist and they want us to do some modeling on it, and then we recognize this shape as looking like the logistic growth model. So then we think, okay, maybe we can like try to fit the logistic growth model to this data to come up with a model of this growth of this cell population. So just to remind you guys, this is the logistic growth model here. I've covered this in a previous video, so if this doesn't look familiar to you, I'm going to put a link in the description to my previous videos on this model. Yeah, if this is looking like strange to you guys, I recommend checking out my previous videos on it. But I'll quickly review now too. So this is just considering some population of cells we're calling X, and this is a model of the growth of this population. So we have two parameters here. We have this R parameter and this K parameter. So the R parameter is the growth rate parameter, and the K parameter is the carrying capacity. So the way this model works is when you're starting out with a small number of cells, this term here will be almost 1 because you'll have a small number of cells. So you have 1 minus some like very small fractions, almost 1. So you have almost 1 times R times X. And then it's like when you have a small number of cells, this kind of is almost exponential growth. But as you get more and more cells, this fraction here becomes larger. So this term here becomes 1 minus some number that's like getting closer and closer to 1 as we have X approaching the carrying capacity. This gets closer and closer to 1. So this whole term here becomes 1 minus some like larger and larger fraction. So this whole term becomes smaller here. So that's what causes the growth to kind of even out as X approaches this carrying capacity. So that's just kind of like a brief review here. Sorry if I kind of like rushed through that, but if you guys want like more of a more thorough explanation, I'll just link you guys to my previous videos covering the basics of this logistic growth model here. But yeah, it's just we have two parameters, R and K. K is the carrying capacity. As the population approaches the carrying capacity, the growth slows down and then evens out. You can think of like when we have X equaling the carrying capacity, this whole thing becomes 0, so we have 0 growth at that point. So yeah, we're going to try to fit this model to this data here. And by fit, again, like I've been saying in these past couple of videos I've made, when we're fitting a model to data, what we're trying to do is estimate the values of these parameters, in this case R and K, these constant parameters. We're trying to estimate the values of those parameters for this model that make it explain the data in the most accurate way possible. We want it to fit the data as closely as possible and figure out what values of these parameters allow for that to happen. And if you guys don't understand what parameter estimation is, I also have like a more in-depth video on that too, covering it as a concept. So I'll also link that in the description. So if you guys want to see that, yeah, I'll put that in the description too. But yeah, okay, so I'll show you guys how to write the Python code for this. And again, I'm sort of like, seems like a bit rushing through this video because I'm hoping that at this point, this is kind of a review for you guys, because I made a couple videos on parameter estimation already. But if any of this is seeming confusing and like not seeming like review, I recommend checking out my like more in-depth video on parameter estimation like as a concept. But yeah, at this point, hoping if you guys are watching this, hopefully it's like kind of review at this point. Oh, maybe I'll just show you guys the actual data first. So this is the actual data set of this data in the plot here. This is the actual data set. It's a CSV where we have a column for time, all the time points where we're taking a measurement, and then the cell counts. And again, we're assuming that this has some like technical noise too, because like of course here it doesn't make sense to have like one cell at the first measurement and then 138 at the next and then 9 at the next after that. It kind of doesn't make sense. So we're assuming that there's some like technical experimental noise here too, like measurement error as well as like biological noise. So we're kind of accounting for like all noise sources. But yeah, over time, the cell population keeps growing, and then eventually hits a carrying capacity that kind of like fluctuates around. Okay, so let's talk about how to write the Python code for this. So the first thing we do, like usual, is just import the libraries we're going to be using. So we're going to be using matplotlib, numpy, csv, and then these two scipy libraries. So we'll just get those imported like usual. And then the next thing we'll do is try to read in this data set. So what we're going to do here is say with open, and then the name of this file, cell count data.csv. We're going to open this as file. Then we're going to define a CSV reader. So we're going to say reader equals csv.reader file delimiter. Sorry, I had to look how to spell that. And this is a comma separated value file, but if this was like a tab separated file, then we just make this a tab, but yeah, we're making it comma for our purposes here. And then it has a header row, so we want to skip over this header, so we're just going to say next reader. That's just how we skip over this header row. And then, so now we want to actually like read in all of our data points. So what we're going to do for this is define some empty lists at the top. So we're going to make a time points list, just start out empty list, and then a cell counts list, also just starting empty list. But then we're going to say for row in reader, time points dot append float row 0, and we need to cast these. Oh, sorry, I spelled that wrong. Sorry. We need to cast everything we're reading in into a float, because if we just read it in without casting, it'll get read in as a string, even though we can see their numbers here and we want them to be numbers. But if we don't cast it, it'll be automatically read in as a string. So we need to make sure we're casting it to a float here. And then we're just going to say also cell counts append float row the second element. That'll get in this cell counts row here. I mean column, cell counts column here. Okay, so this should work to read in our data file here. And then the next thing we're going to do is just to make sure we're reading it in properly, we want to try to just plot the data we're reading in to make sure it makes sense. So I'm going to be a bit lazy here and just copy and paste this code to do the plot. But yeah, I'm just, hopefully this is kind of a review for you guys at this point. But yeah, this is just making a scatter plot of the time points and cell counts. So let's just try seeing what this looks like to make sure we're just reading it in properly. Yeah, okay, let's try, Yep, looks like it's getting read in properly, so it matches our plot. Looks like what it should look like. Okay, so we're in good shape with that at least. So we've now read in all of the data into these time points and cell counts lists. So after this block of code, these lists will be filled up with our actual data points in this CSV. Okay, so now we're ready to start doing the actual fitting. So the first thing we're going to do here is we're going to write the actual ODE function for this logistic growth model. We need to be able to simulate this ODE in Python. And again, I've already made a full in-depth video on this. So if you guys at this point are confused about how to do the ODE simulation of the logistic growth model in Python, I recommend you check out the video I'm going to link in the description to my more in-depth video on ODE simulation of this model. But for now, I'm going to again be a bit lazy and just copy and paste this part of the code in, since this has been covered in a previous video. So this is actually I've actually just copy and pasted this whole function from my previous video, kind of doing the more in-depth explanation of how to do the ODE simulation in Python. But basically, this is just going to let us do an ODE simulation in Python of this model for any given parameter set we decide to pass in for R and K, and any also given initial condition. But yeah, this is just a function for how to do that in Python. It's just using this x SR variable, which will measure the cell population. Then we just pass in some params list that we use to store our R and K values. Can be whatever we want to pass in. And then we just write down the ODE, which write it down and then return it. And this will allow us to simulate this ODE using this scipy.integrate ODE int function. But yeah, so just copy and pasting that for now. But if you guys want more in-depth explanation, I recommend checking out my previous video on it. So the next part is actually specific to this task of parameter estimation. So we need to define our loss function. And the loss function, if you guys have been watching these recent videos I've been making on parameter estimation, every time we do this, we need to write some kind of loss function. And then the way we estimate these parameters is by finding the parameters that minimize this loss function. So this is kind of the most important part with this parameter estimation topic in general, is just being able to write a loss function, which will then be minimizing with respect to the actual data we have. So we're just going to call this loss function, not really trying to be too creative here. And we're going to be passing in our params, time points, and cell counts lists. And this is going to all make sense in a second. But our initial condition is just going to be the first cell count we have. Just going to start our initial condition as the first measurement we have. That's what we want our initial condition to be for when we run the ODE. And then we're going to find some time points to solve the ODE over. So we're going to say here numpy.linspace. And basically, we want to be solving the ODE at every time point to correspond to a time point that we've actually have a measurement for in our data. So basically, the idea here is every time point where we have an actual cell count in the data, we want to also have an ODE model prediction for this time point. So the way we're going to actually write this is numpy.linspace going from the first element of this time points list going to the last element of the time points list, and we want the number of time points called num here to equal the length of this time points list. So if we just write it like this, then we'll have this numpy array t here, which will give us a time point for all the time points that we have measurements for, so that we can basically solve the ODE model at all of these time points to get a model prediction for every time point where we have an experimental measure. Okay, so now we're ready to actually solve the ODE given some params, and also solve it over all of these time points. So the way we're going to write this here is just output equals ODE int. This is this ODE solver we're importing at the top. ODE int. The name of our ODE function, I just called it sim. You guys can call this function like whatever you want here, but we just want to put the name of it here. The initial condition, the time points we're solving over, and then args equals parentheses params comma. Bit of weird syntax here, I know, but yeah, just maybe you can memorize the syntax or just keep, like I'm doing, just keep copying and pasting it. But yeah, this is just how we're passing in our params. And the idea here is we want to be able to solve and get an ODE prediction for any R and K params like pair that we want to evaluate the model at. We want to be able to get the model predictions for any parameter set and get the predictions over these time points where we have experimental measurements. Okay, so now we're going to actually compute the loss for this parameter set we're passing in. So we're going to say loss, we're going to start it equaling 0, but then we're going to say for I in range len time points, basically just going through all the time points where we have an experimental measure, and then we're going to say the actual, data count equals cell counts at this index, meaning at this time point. So this is going to be basically our actual like data measurement of this cell population. This is the actual data value, and then we're going to say model count equals output time point index I, and then we just want to get the first and only column of this output matrix. So this is just giving us for each time point, we want to get the data measurement at that time point and also get the model prediction for this parameter set at that time point. So that's just all we're saying here. And then the next thing to do is compute the residual. So we're going to say res equals, remember here we want the difference between the actual data and our model prediction. We want that difference squared because we're using this thing called the least squares residual minimization. We want the difference to be squared because we could be getting some kind of negative number, and if we get a negative number, we want to make it positive to get positive loss. You know what I mean? But yes, this is just going to be written like data count minus model count, and then square that whole thing. And then we're going to evaluate this at every time point, and at every time point we want to add this residual to our loss. So there's just the loss is going to be a measure of all of the differences squared between our model prediction and the data at each time point. Every time point we're iterating through, we want to add this to the loss. And then after this, we just return the loss. And then we're basically done with this loss function at this point. So now we've written this loss function that for any given parameter set, it will tell us how far off the model is from the actual data. So the idea here with parameter estimation, like I've been saying in all these like recent videos, the idea here is to minimize the loss function. We want to find the parameter set that minimizes this loss function, because by doing that, we'll be finding the parameter set that minimizes how far off the model is from the actual data. And that's how we get our parameter fit here. Okay, so now we've successfully, hopefully successfully written this loss function here. So now I'm again going to be a little bit lazy and just copy and paste in something, but I'll explain this in a second too. Okay, so this is the part that actually does the loss function minimization. So we're going to be using this function called scipy.optimize.fmin. This is a function minimization function. And what we're doing here, this first line here, param 0, this is our initial guess for the params. So this is kind of an art more than a science, but I mean, I guess it's like a science too, but it's kind of an art to be able to like try to come up with a good first guess for your params to feed into the minimization function. So we kind of know that, I mean, I could have made an even better guess, but I don't want to make it too easy. Like, I would guess, like, spoiler alert, but I would guess here that the carrying capacity is something like 2,000. Spoiler alert for that, but I don't want to make it too easy because I want to show that that we actually can like estimate the parameters here. I don't want to just make it too easy. So I just said like 100 for the guess for the carrying capacity. So that's just kind of yeah, I don't want to make it too easy. And I just said for the growth rate initial guess, I just said 1. Because we know that the growth rate isn't going to be like, first of all, it's not going to be anything negative, and then secondly, it's not going to be anything like 1,000 or 1,000,000 or something. So I just said 1 for a guess for the growth rate, and I just said 100 for a guess for the carrying capacity. Even though we can kind of see what it actually is. I don't want to make it too easy. I want to show you guys that it actually can be like estimated here. But yeah, this is just saying our initial guesses for these params. Oh, also something important, make sure you have them in the same order as in the ODE function. So we have the first param being our growth rate parameter R, and the second one being K, the carrying capacity. Just make sure you're keeping the same order here. So the first one being the growth rate guess, and then second one being the carrying capacity guess. And then this line here, a little bit of tough syntax, but yeah, this is how you actually write the error minimization. I mean, sorry, not error. This is how you actually write the loss function minimization. So we're just going to say minimum equals scipy.optimize.fmin. And then we're passing in our loss function, our initial guess for the parameters, and then args. We want to pass in our time points list and our cell counts list. Remember, these are actual lists of data in our data CSV. We've read them into these lists called time points and cell counts. This is just passing in our actual data that we're fitting to. Okay, so at this point, we should be able to get our parameter fits out of this in this this minimum variable here that should contain our parameter fits. But before I actually run this, I want to show you guys the last part of the code, which is how to actually like plot the model fit. So again, I'm going to be a little bit lazy with this point, with this part again, and just kind of copy and paste this block of code in. So sorry for being a little bit lazy in this tutorial, but again, this should all kind of hopefully be a review for you guys at this point. If you guys want more of like an in-depth explanation about this, recommend checking out my like previous couple of videos. But yeah, so this part is just going to be how we actually like plot the fit of the model. We're going to first just unpack this minimum of these which holds our fit parameters here. We just want to get the first element out of that, which is our R parameter fit, and then the second element is our K parameter fit. And then we're just going to put that in a list called params here, just our R fit and then K fit. Our initial condition again is just, we're going to just say that it's the first measurement we have in our data. And then this part here, just defining the time points we're going to be solving over. Just we want to solve from our first experimental time point to our last experimental time point. That's what we're going to solve the ODE function over. And then I just said like 1,000 time points in between. And then we just solve the ODE function over those time points using these fit parameters. And then we're just going to be plotting in red this line that we just plot the fit over. And this will hopefully give us a plot of the fit model over our scatter plot of actual data, so that we can see how it fits the actual scatter plot. So yeah, let me just comment this back in for now, our scatter plot. And then we should, when we run this, if it works properly, we should plot our data and then do this loss function minimization where we fit the parameters to the data, and then do our last plot, which is simulating the ODE using our fit parameters, and then plotting that line on top of the actual scatter plot data. But yeah, so let's just run this and see how it works. Okay, yeah, looks like we got a good fit here. So this is the scatter plot of all of our actual data, similar to what we have. I mean, not similar, but like exactly the same as what we have in this plot here. We just plot all of our actual data points, and then this red line here is the ODE model. This ODE model here, using the fit parameters that we just fit to the data. And if we want to look at those parameters here, this is where I printed the minimum that we're getting out of this loss function minimization. And then so yeah, these numbers here are the fit parameters for R and then K. And we can see here they're in scientific notation here. But this is basically 0.2. That's why it has the E -1. This is just saying 0.2 basically here. And then E3 here, this is saying basically 2000. So these are the fit parameters that our loss function minimization came up with. And then so now that we're at the end of the video, I'll show you guys what parameters I actually used to generate this like fake experimental data set. I'll show you guys what I actually used. So yeah, these are the parameters that I actually used to generate the fake experimental data. I used R equals 0.2 and K equals 2000. So this is like almost exactly what we came up with for our parameter fits. I kind of did this on purpose. I kind of like made like an easy data set that would be like easy to fit to, just to make a video on it. But in real life, it probably is never going to be this easy. It'll be like noisier data, tougher to get a fit, more of like kind of a hassle. Yeah, I don't think you'd be getting like this close of a like nice fit with real data in real life. But yeah, for this video, just made something like easy to fit to for you guys. And yeah, we can see that the loss function minimization basically worked, and we basically came up with like pretty close estimates of the actual parameters that I used to generate the data, which is pretty cool. And yeah, if you guys want to try this for yourself, I'll put all of this code on my GitHub, and I'll put a link to the GitHub in the description. But yeah, I'll include the data set, CSV data set that I have here. Put that up on GitHub, and then I'll also include this file that I used to actually make the data. If you guys want to try like making your own fake data sets to fit to, and then I'll put my my fitting code here too up on GitHub. But yeah, so if you guys have any questions, let me know in the comments, and I'll try to answer questions as best I can. And yeah, thanks for watching, and see you next time.